Today we're going to be learning about mass spectroscopy, which is an experimental method that allows us to measure the different amounts of particles with different masses, essentially is what we're looking at. So we can measure the relative amounts of particles with different masses. Technically, it is a mass to charge ratio, but we usually just consider it to be the mass because the vast majority of the time the charges are going to be +1. Missed a word here, sorry. And so we'll be able to produce a graph of this data is typically how this is analyzed. So the mass spectrum, which is a graph. Not off to a good start here. Oh my gosh, I can't spell. There we go. And so the way that this is done is using a fairly complicated piece of machinery known as a mass spectrometer. And I have a very simplified diagram here of what a mass spectrometer is. So essentially, we have some sample that we're trying to analyze. For our purposes in this course, we're going to stick to elements and mixtures of elements, but mass spec can be used to analyze larger, more complicated compounds. It just gets a lot more complicated to interpret the data as well. There are literally entire courses on mass spectroscopy. So what happens is that our sample starts at the source here. Our sample is introduced into an evacuated chamber. So it starts here, it comes out of the source. This whole thing is like a big tube, essentially. It heads down this tube into the ionizer. So the next thing that happens is as it travels through the ionizer, it gets ionized. So in the ionizer, what we have is a beam of high energy electrons. Essentially strips the electrons off, or strips usually just one, off of your sample particles. So essentially, as your sample travels through the ionizer, an electron gets knocked off by another electron that has a whole lot more energy. So it travels through the ionizer and comes out the other side, now with a positive charge, since it has lost an electron. So we have little positive charged ions moving in this direction. And as they continue to move down this tube here with their charge, they enter a region that has some relatively strong magnets, generating a magnetic field in this area. And a magnetic field and a charge interact with one another. So as your charged particles pass through that magnetic field, their path is altered. They don't continue to travel in a straight line. Their path is bent. So the magnetic field causes our beam of charged particles to curve. And the amount of the curve is related to the mass to charge ratio, like how much it's deflected by. So our particles are going to start to curve around the corner here due to the magnetic field. And then after they get out of the magnetic field, continue in a straight line the rest of the way to the detector, which can tell where on that kind of screen sort of thing a particle hits it. But not all of our particles are deflected by the same amount, is how we're able to tell the difference. So some of our particles will be deflected more. Some of them will be deflected less, that they don't curve as much. So they end up farther over here. So essentially, the lighter a particle is, the easier it is to change its path. The same amount of force applied by the magnetic field is going to change the path of a lighter particle more because it's easier to pull on that. So the ones that kind of curve a tighter corner here are going to be the lightest particles. So the path of lighter particles bends more sharply. And the path of heavier particles doesn't bend as much, is less affected by the magnetic fields. So this is how our mass spectrometer is able to kind of spread out particles according to their mass so that they hit the detector in different locations. And the detector knows what mass to charge ratios will hit where, and is able to like literally count how many particles hit at each different place, which is corresponding to how many particles have each different mass. So the way that this is graphed on a mass spectrum is with mass on the x-axis, usually this is written as m over z, which is just the mass to charge ratio. And the y-axis is relative abundance. So the taller the peak, the more particles of that mass that you had. So a mass spectrum might look something like, usually they're just kind of thin vertical lines. Essentially, they're usually a bar graph. So a mass spectrum might look something like this. Usually you'll have masses labeled on your x-axis, or sometimes the top of the peak will be labeled in the mass as the mass, just so you know kind of exactly where it lies. But we have these different peaks of different heights. So the height of the peak is our abundance, or our number of particles, or is relative to our number of particles of that mass. And the position on the x-axis is the mass of the particle, is how we're interpreting this. So what we can do is use a mass spectrum to identify an element. We know that the mass listed on the periodic table is the average mass of all of the isotopes that exist. So for this element that I've sketched a mass spectrum for here. There are 3 different isotopes with masses of 20, 21, and 22, and we can see that they have different natural abundances, that there's mostly isotope 20, a little bit of 21, and a little bit more of 22. So those averages on the periodic table are a weighted average, and the way that we actually calculate that weighted average is through using mass spec data that gives us the percentage of our stuff that is each of our isotopes as well as the mass. So we're able to calculate the mass that you see on the periodic table. We can also use this data to identify an element, since we do, have the periodic table and already know these masses. I would say that this would be an element that has an atomic mass of a little bit greater than 20. So because this peak is the tallest, our mass is going to be close to 20, but we have some peaks that are a little bit greater in mass than 20. So my weighted average is going to be something a little bit greater than 20. I could look at the periodic table and identify the element from that.